Hello everyone, I'm back with the second video on Cosy, but today it is not the processing video. In this video, I'm gonna show you how to interpret the Cosy spectrum and what is the application of this kind of Cosy spectrum and how you can identify the compound proton position by using this Cosy spectrum. So what is Cosy? So in short, it is um, written as a COSY, COSY, but it is actually called as a correlated spectroscopy. So this is one of the first multidimensional experiments. Cross peaks in COSY are between protons that are coupled. So COSY tells you what proton is coupled to what proton. Protons that are 2, 3 or sometimes 4 bonds apart may show cross peaks. So if you see here, like suppose there are two different carbon have two different proton, in between this proton to the next proton is like 3 bond, 1 2 3. Maximum time it is 3 bond away proton, it's called, like, so this proton to carbon and this carbon to carbon and this carbon to proton, so 3 proton sorry 2 proton 3 bond away. So this can be correlated in their proton spectroscopy. So um, this spectroscopy, Cosy spectroscopy, also known as a two-dimensional spectroscopy, because you will take one proton of the same compound and another proton correlate, and then you will get some peaks. Now, in this spectra, so you will see those, like, through in the square through the diagonal, you will see the diagonal peaks. Those are for those specific proton peaks, and outside the diagonal, those are called like cross peak. So by seeing that cross peak, so and also the diagonal peak, so you can make a correlated or like relation, like which proton is showing this cross peak. So suppose you, if you take this first proton peak here in the diagonal, and if you see, like, there is a cross peak here which is coming from this proton peak, and this proton peak original diagonal peak is this, so ultimately they are related, like they are next to each other. So by this way you can determine, okay, this proton and this proton are next to each other. And remember that diagonal proton cross peak always will be a kind of mirror image, so you can also think this is the same peak. So this is the cross peak for this first one, which is correlated with the second diagonal peak, second peak, second proton diagonal peak. So let's see more details. So suppose this is a compound, and this compound is a symmetric molecule and it has a single bond, so it can rotate. So since it can rotate through the single bond, so these protons, especially these two protons, they can change their position once they are inward, like parallelly to the benzene ring, and also sometimes away from the benzene ring. So that's why they give like kind of average peak for them, like we cannot determine which peak is what, but to determine their rotation and activation energy, so we can freeze their rotation. So we can take the NMR of that molecule at minus temperature. So let's see, uh, this is the same compound. We have taken the NMR at minus 90 degrees Celsius. That means this rotation between the carbon-carbon single bond freezed, and it gives like separated peaks for all those protons. So here we are seeing 1 2 3 4 5 6 7 8 proton. So here, if we number start if we start the numbering from here, like 1, then it could be 2 3 4 5 6 7 8. So here, I'm showing the aromatic part. So this is number 1 proton, and this is number 2 proton, and this signal is 2. You may ask, like, why it is 2, why not this one? So I'll explain. And see, number 1 has one neighboring, so it is a doublet, and number 2 has two neighboring protons, so it is a triplet, and number 3 also has two neighbor, 1 and 2, so it is another triplet. So but you can ask like why it is not 2, because it is also has a two neighbor triplet. So that's what we can determine through the cozy NMR. I will explain. So this is number 3, and next is number 4. Again, number 4 proton has a one neighboring proton, so it is a doublet. And then number 6 and 7 will be like this. They will merge together. And why these are 6 7 and how they are different, that's what you can determine through the cozy like 2D NMR. And this is number 5, and the last one is number 8. So let's go to the cozy 2D NMR to see how they are identified or correlated. So this is the cozy 2D NMR, and now if you see the number 1 and number 1, and this is the number 1 diagonal peak. Remember, diagonal peak is the like real peak, main peak, but when that diagonal peak is related with the cross peak, so that means that cross peak directed diagonal peak is the correlated peak. That means they are next to each other. So that's why number 2 is this triplet, and they have a cross peak, so 1 and 2 is next to each other. So doublet and triplet and 1 and 2, and they have a cross peak here, like it is like a mirror image. So then now, since you know already number 2 is there, and number 3 will be next to the 2, and every bond is like 3 bond, 1 2 3, 1 2 3, so 3 bond. So that's why you can easily find this proton like number 3 proton, and that is a triplet, and also that has a cross peak with it number 2. So number 3 is done. So now find out the number 4. So number 4 should be a doublet and also next to the 3. So these 3 has a another cross peak here. So that cross peak is like this. So that is a number 4 proton. So for the first ring, 1 2 3 4, you already get it. So number for the next ring, you are saying like 6 and 7 here. Like why I'm putting 6 7, why not like 5 and 6? Like 5 could be there. So 5 is a doublet, and 8 also will give you a doublet. So there are two doublet there, and 6 could be triplet, 7 could be triplet, and they are very next to each other. That's why they are giving merged proton peak. So still it is not like good evidence. So you can find one thing. So 6 and 7, just you can, since they are merged, you can think of like this is your diagonal, this is the diagonal peak for 6 and 7, and also the cross peak like very small. But now you can think of like, since 6 is next to 5 and 5 is a doublet, so you can think, see, this is the 5, it has a cross peak that is with the 6, okay, and since 7 is also here like with the 6 and 7, and next to 7 there is another peak called like another proton 8, so that is also correlating here at the last point, so 8. So that's why you can think, if you take that is a 7, then that will not be correlated with the 7. So again, that could be also, that could be like if you think this is 7 and 6 is relating, so 6 and 7, but in that case, and here like 6 and 8, that is not possible because 6 and 8 away. That's why like you can think like this is 6 and 7, and this is 5, so 6 is connecting with the 7, and also 7 here, same position, 7 is connecting with the 8 because triple 3 bond away coupling. So this can be also, this part also can be confirmed by taking nosy like space correlation. So nosy actually based on the space correlation, I will discuss later on in another video. So this is how you can identify all the protons for any specific molecules. The cozy also can be very complicated for any other molecules, small drug molecules like natural product molecules, complex molecule. So that's how people use 2D cozy NMR to get the first impression of the protons relation, like between the proton bit next to the another proton. So I hope till now you will understand how to interpret the cozy NMR to the NMR. If you have any question, ask me in the comments. I will try to answer, or I will give the literature or like link to understand more of it. And I will bring new videos. Until then, stay safe and please subscribe my channel to get the new videos.